Guide to EAA. Part 2, The Basics, Equipment and Processing. In Part 2, we're going to cover some basic setups. We'll also talk about some of the equipment needed, and we'll provide a high-level view of the basic concepts and processes that you'll need to understand for doing EAA. The basic setups. Our first basic setup comes from the traditional days of video astronomy, where some sort of video or security camera was used. Power needed to be provided directly to the camera from some other source. The analog signal came out of the camera via some sort of cable TV connector or an RCA phono type jack. That signal was then sent to a TV or some sort of monitor for viewing. Control of the camera was usually accomplished via buttons on the back of the camera, or sometimes through a remote that had another wired connection into the back of the camera. So our next setup builds upon our previous example by replacing the TV monitor with a computer. Here, the analog video signal from the camera is sent to a video grabber, which then converts that analog signal out to a digital signal, which can then be sent to a computer through some sort of USB connection. And this allowed the observer to further enhance the signal or record the object directly to the computer. And then our last example is where I think video astronomy becomes EAA, at least in my opinion. We've removed the analog signals and now we're controlling the camera via a computer. We've also simplified connections in that there's only one cable. This is pretty much the current state of most of the common EAA setups. What equipment is needed? Cameras. Well, my recommendation is to start with what you've got. And just about everyone today has a smartphone. You can use that smartphone along with some sort of an adapter to record views directly from your telescope. Now, many folks also have DSLRs, and most of these DSLRs have video mode. Additionally, there is software available that can stack images from a DSLR in real time. And then we have an option of a dedicated astronomy camera, and I think this is an excellent option. It's fully computer controlled. The observer can enhance the images captured via options like integration, exposure time. You can adjust the balance of color, the gain, the gamma, and you can even start to play around with some of the light curves if your software has that capability. If you're just starting out and want to save some money, or maybe you're unsure if EAA is the direction you want to go, you can pick up a Celestron NeXYZ smartphone adapter. And you can use that with your existing smartphone and eyepieces. The CMOS chips in today's smartphones are actually really good. However, doing this sort of afocal projection can have some challenges, especially getting the proper placement of the camera over the eyepiece. Another inexpensive option is to purchase a CCD camera kit like the Revolution 2 Imager. These are inexpensive, costing around $300, and you don't need a computer. Unfortunately, the resolution is sort of low at 720 by 576 pixels, and it does have a higher read noise than other options. Now, these used to be my recommendations. However, in recent years, smart telescopes have come a very long way and may now be the best value that's available. Some are actually under $500, but between inflation and tariffs, the prices are going up. A compatible smartphone or tablet is needed, and I highly recommend using a tablet over a smartphone so you can really enjoy those views. They have sensitive camera chips and have some really good high resolution. They enable you to edit and enhance in real time, and they're great for wide angles, but they do perform poorly on small objects like planets. And most are fully automated and will self-align, and some will even autofocus. Now, if you want some higher quality pictures, I would recommend going with a dedicated astronomy camera. They have phenomenal CMOS chips, and you get to leverage your existing astronomy equipment, and this is especially good if you have some high-end equipment. a computer and software is needed, and again, with these camera chips you get higher resolution and low read noise. Now, it is important to understand these aren't as sensitive as CCD chips, so your exposures are going to take a little bit more time, but the rewards are definitely there. Telescopes. Just about any telescope will do, just so long as it can reach focus with your camera. Now, you want to make sure that your telescope and focuser can actually take the weight of your camera plus any other gear, such as focal reducers and filters. Be very, very wary of plastic or cheaper focusers. In the pictures that I have on the screen, the one on the left-hand side you'll see is a very narrow focuser. In this case, it's made out of plastic. It has plastic teeth, and if you put anything heavy on the back of that focuser, when you tilt the telescope up, that camera will just slide out and, God forbid, fall on the ground and get damaged. On the right-hand side, I've got an image of the Feather Touch focuser. This is an all aluminum focuser, super high end, but this is an example of the sort of focuser you're going to want, and it has a nice ability where you can actually get fine focus and then use a set screw to actually then kind of hold the focus in place, and your camera and other gear aren't going to slide out of the tube. Now, aperture is less important than focal length when you're doing EAA. So just like in astrophotography, the shorter your focal length, in other words, the faster your telescope is, the quicker that you will actually acquire images. Now, the longer the focal length of your scope, the narrower the resulting field of view is going to be of your object given the same camera. I would highly recommend that you use some field of view calculators online so you can actually go ahead and simulate what your views are going to be like. And I'll drop a link in the description of some good tools to use. Now, Schmidt-Cassegrain telescopes can provide some focal length flexibility. Long focal length for very small objects like planets. You can put in focal reducers for some medium-sized objects, and if you have the right type of SCT that is FastStar compatible, you can actually use something called Hyperstar and get down to what's called a focal ratio of f2 for some really wide field images. Now, the larger your telescope aperture, the more susceptible it is to issues with light pollution, moon glow, and atmospheric disturbances. So again, I've got to take all that into consideration. In terms of mounts, it's important to understand how the two main types of telescope mounts work to track celestial objects throughout the night. So these objects appear to move in arcs across the sky and not in straight lines. In reality, it's us here on the surface of the Earth that are moving as the Earth rotates along its axis. Now, in our first example here, we've got an alt-az mount, which is short for altitude and azimuth. And the mount moves the scope up and down or left and right. Now, once you're on an object and locked, you need to move your telescope up and over or over and down, depending upon where you are in the sky, just so you can track the object. And so as we're doing that in this particular example, pay attention to how the telescope kind of slews through the sky, how your view changes in the telescope. You can see the view of the moon rotating. Now, in our second example, we've got an equatorial mount. And the two most common forms are a German equatorial mount, or a GEM, and an equatorial wedge. Now, once you're on an object here, the mount only needs to move in one direction, and that's called right ascension, in order to track the object. And this, of course, assumes that you've correctly polar aligned the telescope. Now, in this scenario, notice how the view through the telescope, our moon here, as the telescope pans across the sky, the view does not change. It does not rotate. Now, alt-az mounts are much easier to set up, but generally don't offer the same sort of precision in tracking as an equatorial mount. The type of mount that you're going to want to use is going to depend a lot on what objects you're viewing and how dim or bright they are. And when I talk about some of these exposures, I'm referring specifically to the capture of a single exposure and not necessarily the total exposure through multiple snapshots. Now, for single exposures less than 15 seconds, pretty much any alt-azimuth tracking mount is going to be fine. You won't notice that field rotation. However, if you go beyond 15 seconds, you will start to notice that your stars towards the edge of your view in the camera are going to start to streak because of that rotation. It may seem hard to believe, but in just 15 seconds, you'll be able to see that streaking. Now, for the brightest objects, so if you're going after the moon or some other things, even a manual alt-az mount can work if you're actually taking video. You can actually just kind of slowly move it along and still capture that object. And there are quite a few packages today that will compensate for any sort of tracking errors or field rotations. So even on some of my telescopes, I can take 5 to 10 minute total exposures because the software itself will account for the field rotation. I will get some wonky looking triangles as each individual snapshot does show some rotation, but it's able to stack and align it perfectly. You just wind up cropping out the edges a little bit. A few minutes ago, we discussed telescopes and mentioned focal reducers. So whether for a refractor or a Schmidt-Cassegrain telescope, focal reducers can provide some flexibility in altering your field of view for your given telescope and camera. So you've got Barlows that will increase your magnification and shrink your field of view, which are great for planets. Then can use some focal reducers. A very standard, almost ubiquitous version is the 0.63 standard for an SCT. It just screws right onto the back of your visual back. You can find 0.5 times focal reducers both in a 1.25 inches and in 2 inches. And for SCTs that do have what's called the fast star system, you can actually mount what's called a hyperstar on the front, and you can get down to f2, or in this case, you can be at a 0.2 times focal reduction. Now, you can also put together variable options, and a lot of these are DIY, and they will alter how much focal reduction you're getting just by adding or removing spacers. Now, to give you an idea of what Barlows and focal reducers can do for changing your field of view, I'm going to use an example of my 1-inch SCT using different pieces. So the first one is if I'm using a 2x Barlow, my field of view is going to be about 7 minutes by 7 minutes. So that's a very, very small field of view. Now, if I'm using it in native format, so at f10, field of view is just under 14 by 14 minutes. If I'm using my 0.63 reducer, my field of view is getting a little bit larger. In this case, it's a little over 22 by 22 minutes. And then if I am using a reducer that does 0.4, now I'm a bit more than half a degree, or in this case, just shy of 35 minutes by 35 minutes. And then if I'm using my hyperstar, I'm actually at a little over a degree field of view at 1 degree and 9.6 minutes. Since EAA is about using technology and electronics to enhance your observations, you actually need something to view the object on. And your options are going to depend on what other equipment you're using. If you're doing afocal projection from an eyepiece to a smartphone, you can pretty much skip what I'm talking about in this section. But if you're using a modified security camera or a Revolution 2 imager, you'll need a monitor that accepts some sort of AV or an analog signal. And if you're using an astronomy camera, you'll need a computer and a monitor. Often a laptop is ideal in these scenarios because you'll have your computer, keyboard, mouse, monitor, and power source all kind of contained in one piece of equipment. But there are many, many options out there. For me, I personally use a Melee Quieter 4C. It's a mini PC that is powered by a 12-volt USB-C power delivery connection and a portable Virzin computer monitor that is also USB-C power delivery. So back in the day, when we were using only modified security cameras, you had to use a video grabber if you wanted to use a laptop to view or save images from your camera. For the most part, they are a thing of the past, unless you're using a camera with an analog out connection and you want to use a computer. Their function is pretty simple. They convert an analog signal to a digital signal and then send it via USB to your computer. And in my experience, I've noticed what appeared to be some rather kind of hot pixels, but these would blink on and off, and not sure exactly what was causing it, but I attributed these anomalies that were created by the analog to digital conversion process. Now, in terms of software, this is certainly not an extensive list, but I've tried to provide a list of some of the more common applications, both in the past and present. So you've got the software package MiloStick, and that is something that is only used by Malin cameras. Another piece of software that was very, very highly regarded back in the day is Infinity software, and it was used with only some of the ATIC cameras, and again, proprietary to those cameras. You've got Lodestar Live, which is only for Starlight Express cameras. Now we've got something that's somewhat new. It is called Astro Live Stacker. This is new software out of France. Unfortunately, I have not had an opportunity to play around with it, but I have heard it's pretty good. And then we have SharpCap, which is my preference, and I'd like to think that it is the king of the EAA software. It is very popular. Some versions are free, but even the full-blown version, I think, is about $15 per year, and I believe there also is an option to purchase a lifetime subscription. What I really like about SharpCap is it's extremely powerful. It does a lot of things, and the developer is constantly making improvements and adding features to it. So again, in my opinion, I think it is the best software out there. Next we have Astro Toaster, and this is specifically designed for DSLR and CCD cameras. And then we have ZWO's ASI Air, and this is for ZWO cameras only, but it does pretty much control everything. So if you have ZWO equipment, not just a camera, but you've got their mount and all kinds of other things, it will control everything. And it is pretty good. In fact, I'd say very good, but in my opinion, SharpCap still does a better job in terms of live stacking and getting that kind of final EAA view. So who doesn't love accessories? These are some items you should seriously consider, as they will greatly improve your overall experience. So some sort of light control or control room. Now, for a laptop or a monitor, you can get a small tent or a shield, or in this case, I'm showing an example of something called a lap dome. You can try small tents, shelters, or blinds. And in the past, I've used an ice fishing shelter to help keep all stray light at bay. And you can also consider doing some sort of remote control from inside an RV, or if you're at home and want to stay nice and warm, you can do it from inside your house. And in terms of focus and getting focus, something to consider are focus masks. They help get focus very, very precise. And also, you should consider using a motorized focuser. There's nothing more tedious than having to jump around from place to place, turn your focus knob, and then run back to your monitor to see if it's in focus, and having to run back again, make a small tweak, come back, and it's a lot of back and forth. Having a motorized focuser that you can control right from your computer as you're viewing the image makes an enormous difference in your enjoyment. And if you're planning on doing EAA from a location where power may not easily be available, you should consider building a field power / battery box. Okay, in summary, as for a camera, go ahead and use what you have for now. Personally, I like using dedicated astronomy cameras as they allow for the best flexibility and the easiest attachment to telescopes. I'm currently using a ZWO ASI 533 MC Pro and absolutely love the sensor size, the sensitivity. It's great. In terms of a telescope, make sure that it can reach focus with your camera and that it's got a sturdy focuser. You want to understand your scope's focal length and how it's going to impact your field of view with the camera that you've selected. SCTs will provide some more flexibility than other scope designs. If I had to kind of pick a scope now, it would be either a Celestron C6 or a C8. They're just the right size in terms of portability, but you still get some aperture and great for EAA. In terms of mount, I highly recommend that you get a tracking mount. Go-to mounts make EAA so much easier. And if you're going to be doing exposures longer than 15 seconds, you definitely want a good equatorial mount. And I would recommend going with a good German equatorial mount, as they tend to be a little bit easier to set up and a little bit easier to transport than, let's say, a wedge-mounted telescope. In terms of some of the other things to consider, you'll want to make sure you've got a good computer monitor combo. You need to see what you're capturing. I personally like the portable monitor and using the Melee Quieter brand of mini PCs. You'll definitely want to use focal reducers for SCTs to maximize the flexibility of your field of view. Focus mask and a motorized focuser are huge time savers. You can pretty much get all kinds of focus masks. I recommend the batten off type. And in terms of motorized focusers, ZWO, electronic automated focuser, and the Gemini electronic automated focuser are two really good options. And you want to make sure you know how much power that you're going to need and either buy or build some sort of power distribution box or field power to match. And of course, be a good Astro neighbor, shield your monitor. I highly recommend the Lap Dome, fantastic product. You can just Google that. And last but not least, especially if you're just getting started, a smart telescope covers a lot of the above in one turnkey package. And I would highly recommend either the ZWO S30 Pro or the soon-to-be released S50 Pro, or you can check out some of the Dwarf Labs offerings as well. Also very good smart telescopes. Basic EAA concepts. Keep this a secret, but we're going to give you the perfect solution for EAA, and that is that there is no perfect or best solution. There will always be a compromise. Not one solution out there is going to necessarily be better than another. You have to determine what's going to work best for you and your circumstances. Now, your goals and circumstances are going to change over time, and your equipment will need to adapt and change as well. So my recommendation is not to spend a lot of time trying to future-proof whatever you want to purchase or need to pick up and kind of get stuck in that paralysis by analysis. Now, that said, EAA can be simplified into two rather straightforward steps. And that is that the goal of EAA is to capture an image of an object that is brighter, more colorful, and more detailed than we can see through the same telescope just by using an eyepiece. Now, if you saw part 1, the video in this EAA series called What is EAA, then you might recall this comparison of the Ring Nebula M57 with a sketch through a 14-inch SCT from a dark sky being compared to, on the right-hand side, a smaller 11-inch telescope from a suburban site, and that 20-second snapshot using a CCD camera. In the EAA version on the right, we're picking up stars that are 18 times dimmer than what that person saw through their eyepiece in a larger scope from larger skies. And of course, this is accomplished with the aid of a camera. Now, the camera is going to collect light via its sensor or its chip over a specified time to make a single image, and this is known as an exposure. Now, the longer your exposure, the more light and the more data is being captured, and thus the brighter and more colorful and more detailed your view is going to be. However, the longer your exposure, the more likely the resulting image might be negatively affected by any sort of electronic noise from the camera. You might encounter some tracking issues or limitations with your mount, or there might be other objects interfering with your exposure, like satellites or anything else, airplanes coming through your field of view. Noise from our cameras, mounts, and sky conditions will all contribute to limiting the length of a single exposure that we can capture, and therefore limiting the brightness, color, and details of our image. However, we have an ace up our sleeve, and it's called stacking. Stacking is literally what it sounds like. The camera takes single exposure after single exposure and adds each one of the images on top of one another. The data, or photons, of each exposure are added up into that one final image. For example, a stack of 6 10-second exposures is like one 60-second exposure. Both have a total exposure time of 60 seconds. Although that's not exactly a true comparison because there are some diminishing returns, the concept and comparison is sound. The process of stacking exposures can be categorized into two broad buckets. The first is done in camera, and that's called integration or hardware stacking. The second is done outside of the camera and is often referred to as software stacking or just stacking. Now, I'm going to pause here for part 2 of this guide to EAA because the devil is really in the details, and while this particular video was to try and provide a clear summary of the process, the specific steps to achieve brighter, more colorful, and more detailed views can get really confusing, especially once we start talking about different camera models and different software packages. So, subscribe to my YouTube channel as I'll be creating more videos on EAA, and we'll also be doing a demo of how to do EAA with SharpCap, and I'll also be live streaming some of my observations. I also highly recommend getting active in the EAA section of the website cloudynights.com. Read up on the topics there and ask questions. Also, get outside and experiment with your gear, and make sure you check out any local resources that might be available to you, like astronomy clubs and planetariums. Thanks for watching.